All right. So, how about this for, we'll do like time, and we'll do maybe like 24 hours, and I'm going to do temperature. And let's say there's 0, I don't know what this is. Maybe that's around 50. Okay. And would you be okay if I said like the temperature looks maybe like this? Does that look reasonable? Makes sense. It sort of goes down. Maybe this is hours past midnight. Goes down at night, warms up in the middle of the day, and then goes down again. So, what do they mean when they say the average temperature today was 43 degrees? What does that mean?
Every temperature divided by how many temperatures there were.
All right, so Betsy's saying add up all the temperatures there were and divide by however many there were. How many temperatures were there?
A lot.
Yeah, how many?
Well,
Probably just take every hour.
What?
Probably just take every hour.
Take every hour?
But how do you know?
So take 24 temperatures?
Well, in the day or like night, are you?
over
I
24
don't know. Don't they tell you the average temperature today was 43 degrees?
They usually have a day temperature or a night temperature.
All right, fine. The average daily temperature today was,
It'd be like
what does it
however
mean?
many times during the light. I don't know the temperature when the sun's out.
Every time it changes?
Wait, don't they show you that's what I was saying.
So people feel good about saying the every hour thing?
Yeah.
Is that what the National Weather whoever does?
Yeah.
Or do they do it every half hour because they're really good?
And now do it every 15 minutes.
Every 15 minutes?
Yeah.
All right, well, let's take this idea and extend it a little bit into calculus. What if I said, look, temperature is a continuous function, right? Temperature is continuous. It's the only thing, I guess, that's discrete is how we measure it. Like, we measure it by what? Degrees. But you could actually, if you wanted to, measure it by tenths of degrees, or hundredths, or thousandths. Or if you had instruments accurate enough, you could actually measure it continuously, right?
What do you mean,
Like
6.5 degrees?
Mm-hmm. Or 6.57392, or root 2 degrees. Okay. What if I said what we should do is add up all of the temperatures? Like, what if I said add up all the temperatures for this day? How would you do it?
As a, what's it called, an integral.
That's totally what it is. All right.
Take the start and end.
Yeah. So, look, if this is the temperature function, can I do this? Is that all right?
Yeah.
Temperature is a function of time. All right, if we want to add them all up, what adds? The definite integral. So let's add up from 0 to 24 all of the temperatures. That will add up all the temperatures for this, whatever this function is. But there's a second part to someone said about taking the average. You have to add them up and then divide. And in this case, we have 24 hours worth of temperatures. So if the weather people wanted to, that's how they could find the average temperature. The average value for a temperature is the integral over the interval. And we're going to use this a little bit. So if we want, in general, the average value of a function, now, it could be, like if there was just 2 or 3 values, we could add them up and divide by 3, right? But if we have an infinite number, we can actually take the integral and divide it by the interval. So the average value of a function is the integral over the interval. I think the book writes it like this. Are we okay? That's the same thing. Get out your classwork. Let's see. All right, Liz, read for us. 13, sorry. Oh, come on, that's hilarious. Yeah, now you got it. All right, so grab your calculators. A says find rota's velocity at t equals 1 and t equals 17. Boys, you can do t equals 1, and girls, you can do t equals 17, and we'll divide and conquer this problem. All right. What do we have for t equals 1?
5.7.
Do I have a second on that?
Yeah.
For real?
Yes.
What are the units?
5.7 feet per second.
Feet per second. 17? 15.3. Do I have a second on that? Meters per second. Okay. And that sort of looks like what the graph would be, right? I mean, doesn't the graph look like it's a little bit above 5 here, and for 17, like about 15-ish for 17 seconds? Is that all right? Find rota's displacement. Oh, you're right. Sorry. I was in physics class, Liz. We were there together. Feet. There we go. Feet per second. Find rota's displacement from 1 to 17 seconds. I'll give you like 30 seconds to do it. Think about it. Think about the easiest way you know how to. And if you can't think of easy ways, think about more challenging ways you know how to. Whoops. And then after you get it, think about all the ways you could get it, because I'm going to say, what'd you get? And then I'm going to say, how'd you get it? And then I'm going to say, what other ways could you have done? That means if he were standing there. Am I that loud? Sometimes, maybe. Derek, you feeling good, bad, or ugly about this? I can't see the hand. Would the hand do it like this? No, definitely not. All right. Tolly, good, bad, or ugly about this?
Not so good.
Do you want to do a courage for the deed thing, or not really?
Well, I just displacement word choice.
Displacement word choice? That's not even a sentence.
No.
What? It's a fragment.
I'm sorry.
Distance, if that helps.
Oh, okay. How much she went?
Yep.
Because displacement sounds like she got lost.
Okay.
I'm sorry. I confused me. Okay.
So do you want to answer the question now, or not
Okay,
really?
Well then, yeah. I mean, you could just look at the values.
Take the thing.
Okay.
Come on.
I'm sorry. No, what you would do is you take 1 to 17, you see what the values are. I guess you could do that would be 17 intervals in between. That would be really tedious.
Okay. So, fine. Absolutely. I like it. All right. Zach, another way? All right. Big old triangle. Now, I have to be honest. I see this as a triangle with some edges cut off. Like, did you do 0 to 20 instead of 1 to 17? You did 1 to 17? So how's that a triangle? You did like this?
I did displacement just a straight line curve, so it's just the hypotenuse.
You did this?
Yeah.
Mm-mm. No dice. Gabby?
Well, I just did num, and then I just plugged in 1, 17, and then I just did 20 intervals. I don't know, I just thought that'd get me closer, and then I looked at track because I know that's the average.
All right. So you can use numInt.
Yeah.
What else? No, you all are driving me a little bit crazy. So look, Tolly's saying you can count up the squares, do rectangles or whatever. Gabby's saying you can do numInt. You got some really clever ways of doing it, Will.
Math 9.
Math 9? All right, FN int, that'll totally do it. Now you're saying yes, Adrian? Where were you 2 minutes ago? And they are a bunch of trapezoids. You could actually make these into a ton of trapezoidal-like figures, right? But I would agree with Tali. I think that's tedious. I think Math 9 or Calc 7? Did anyone do Calc 7? No one did Calc 7.
I'm doing it right now.
All right, good. You have these great tools at your disposal to approximate definite integrals. And I'm going to be honest, counting squares is okay, making geometric shapes is okay, but if you really get down to it, I want to do something that's like quick and easy, like using Math 9 or Calc 7 or NumInt or RSum. I'd even say, though, if you have your choice of Calc 7 or Math 9, they're better than RSum or NumInt. All right, so enough with these trapezoids. What do we get? 372.8. Do I have a second on that?
Yep.
And what are the units on that? It is feet, because each block is feet per second by second, so you get feet. All right. So, Jack, read for us C.
Her average velocity on interval 1 to 17 is her displacement for that interval divided by the number of seconds in that interval. Find her average velocity on 1 to 17.
All right, so she went a total of 372.8 feet. How many seconds was she riding for? I got like 3 different answers there. 16? Because she was riding from 1 to 17 seconds, which is 16 seconds. Okay, so let's do 372.8 divided by 16, and what do you get? 23.3?
Yeah.
23.3. I have a question. What are the units on that? Because she went 327 feet divided by second. So now we're back to an average rate. So that's actually her average value. And if, actually take a look. Can you add 5.7 plus 15.3, divide by 2 and get 23.3? No way. So it's not just the average of the endpoints. You can't take the average of the endpoints and say, oh yeah, that's her average value. And can you see by the graph why? Like, can you see it goes above that? So if you look at this entire area, that's the blue. I'm going to draw a rectangle in red. And the rectangle is going to be 16 wide and about 23 high. And what I actually would like to claim is that the area in the red rectangle is the same as the area in the blue. Is that a believable statement? Mm-hmm. So look, Rhoda could either ride like she did and cover 372 feet, 372.8 feet, or if she wanted to just ride, if her motorcycle only had one speed, she could set her speed to 23.3 and cover the same amount of distance. And that's her average value. And it's very similar to what we're doing with temperature. If we go back, give me a sec, I know you got something, but if we go back to the... Oh yeah, of course. If you go back to the temperature, when we were measuring there's some average temperature, and that would represent if the day didn't want to warm up and cool off and stay at one temperature for the whole day, that's what it would be. Just out of curiosity, we measure, what's the definite integral in this of this temperature and time graph? What are the units in the numerator? Degree hours. That's a weird unit, don't you think? Degree hours. But then we divide it by hours, and we end up with an average temperature in degrees. So that actually worked out. Do you want to ask a question? Do you see how those two things fit together, or is that like a little forced? A little forced? It was all right.
Are you getting 23 from the average?
Yeah, 23.3 feet per second is the integral. That's what Will told us to do over the interval, which is Zach said 16 seconds. So it is the integral over the interval. All right. So if I had to say one thing today, Jack, average value is the integral over the interval, and that means a lot. Let's think about your grades. This is you in first semester, right? And then second semester comes along. Looks something like that, right? Now look, here you are hanging out at 100, and here you are with a 0. Now, if I said, hey, let's just average, you started off the year with 100, and you ended the year with a 0, so your average should be a 50. That's not fair, right? Not fair because not only do you not want an average of 50, but look at your achievement. Don't you think your achievement says that you were doing well for a lot longer than half the year before you just totally tanked? So if you were a smart calculus student, you'd say, hey, Mr. B, you should really take the definite integral of my achievement curve and divide by the number of days that we've had school, and then that'll be a fair assessment. As a matter of fact, I don't know if you can, but can you actually think about the average value here might look something like this blue box? Can you see that the blue rectangle might have the same area as the red?
Yes.
And so you'd say, hey, look, that's like an 80. That's what my average value should be. Give me an 80. Give me a B minus, not a 50. That's not fair. And you're a calc teacher to boot. Is that all right? So there's this power of finding averages using calculus. Finding averages using calculus doesn't mean take 2 and divide by 2. It means you can take an infinite number of values and divide over the course of however long you're measuring the values. All right. All right. Questions, comments, considerations? All right. All right. Do this quickly for me, like in 10 seconds. Come on. You're going to use your calculator. What'd you get?
2 points.
All right, about 2 1/3. How'd you get it, Betsy? Nummint. Okay, so either Nummint, Math 9, Calc 7, one of those. Okay. Let's see. Whoops. X squared, and we can do like a zoom decimal. And I'm sort of a fan of Calc 7. It's a very visual thing, so between 1 and 2, you get 2 1/3. Okay? Can you tell me what this is the derivative of? What's x squared the derivative of? What's it the derivative of, Derek?
1/3.
You agree with him? Okay. I actually think that if you took a look, a little bit of a new notation, I'm drawing a bar, I've never done that before. If you looked between 1 and 2 for 1/3 x cubed, if you plug 2 into the function, what do you get?
2 point, probably 2 point, 2 1/3.
2 1/3? 8/3? And if you plug... That's not how it
You get
works.
1/3. Right.
Oh, that's 2 2/3. Yeah, if you plug 1 in, what do you get?
1/3.
1/3. How much did the function change between 2 and 1? 7/3? Hey, what's 7/3 the same as?
2
2 1/3. So do you remember on Friday when we said the function changes exactly as much as the definite integral of the derivative. And guess what? After Derek told us that this is the function that x squared is the derivative of, we didn't need our calculators. We didn't need numint, we didn't need calc 7, we didn't need math 9. So this should be the beginning of you seeing that you could either take the definite integral of a derivative, or if you know what the function is, you can plug values into the function. Now, if I had to go tell like a 7th grader what to do, would it be easier to explain numint and calc 7 or how to plug numbers into a function? Plug numbers into a function. This is easy. This doesn't need a calculator.
You have to have only one interval for that.
Say what you mean? I don't know what you mean. Say.
Like that doesn't work if it's more than one interval.
Like if it's 1 to 4?
Yeah.
Let's try it. Go ahead. Do that on your calculator. Tell me what you get. Uh, 4 times 4, 8, 64. So about 20. Do I have a second on 20? Anyone? 21. Oh, 20. Oh, 1. 21. All right. So if I plug 4 into Derek's function, I get 4 times 4. Whoops, that's not 64. 4 times 4. Oh, yeah, it is. Times 4. Is that 64? And when I plug in 1, I get 1/3. So I would get 61 thirds.
63 thirds.
Thanks. Hey, guess what 63 thirds is? So if you know what this is the derivative of, the function changes the same amount as the definite integral of the derivative. Yeah, that's totally true. Betsy gives us the real problem, the real snag with this. Can we just... Well, all right, we have like a minute. What if I said, like... do you know what cosine's the derivative of?
Yeah.
What's sine? So if you actually knew... Hold on, one more.
The limit does not exist.
No. Oh, gosh.
Got him.
Yeah. Look at how good that... You're good at this.